Hey guys, I want to make a quick video for the day 4 material. So the big part of this is I want you to work in the measurement lab. There's a PDF. You can do this on Notability, or you can print it out and work on it. I also have a folder with all the images for the measurement lab. So if you notice when you open up the measurement lab, it's going to be several devices that you're asked to measure. And so when you open up the folder, all of those images will be in that folder, and you can work through each image and take the measurement. So I'm hoping that takes maybe 20 minutes or so of your 30 minutes. In terms of some material that I would like you to transcribe and to put into your notes, we're going to talk about units, precision and accuracy, significant figures, and then some of the rules for it. Now, don't worry too much. We will revisit a lot of this in class next week on day 5 and day 6. So, but I just want to hit on this a little bit in a brief lecture. So again, units of measurement. So we have our standard units in science. We have our quantity, the unit and symbol. So we have length, the base unit being the meter, the symbol being lowercase m, mass, kilogram, kg, time in seconds, symbol S, temperature in Kelvin. You've probably never seen that before. That is the SI unit. We're not going to really use Kelvin until a little bit later this year, but that is actually a standard unit for temperature. The symbol is capital K. The amount of a substance is called the mole. We'll talk about that later this year. The symbol MOL or MOLE I've seen. And then these are non-standard units, but they're very common in chemistry. So volume, liters, capital L. Milliliters is also very common. So instead of liters, we oftentimes encounter milliliters. Again, 1,000 milliliters to a liter. Temperature, oftentimes instead of Kelvin, we're using degrees Celsius. Fahrenheit, you don't see a whole lot in chemistry. Concentration, the unit is molarity, capital M. Pressure, we have the atmosphere, millimeters mercury, and the torr. The most common, probably the atmosphere in millimeters mercury. You don't see torr so often. So I just want to hit on that just so you're aware of some of the most common units we see in chemistry. Now there will be others, but these by far are going to be 80–90% of what we see this year. Precision and accuracy. So a couple ways to think about precision. Number one has to do with when you're in lab, when you take measurements. Precision has to do, by definition, how close those measurements are to one another. So, for example, if you took 5 measurements of 5 centimeters, 6 centimeters, 5 centimeters, 5 centimeters, and 6, we would say that's fairly precise because those measurements are very close together. If you're in lab and you took measurements and they were 5, 10, 50, and 100, we would say those measurements are less precise because they're not as close to one another. Precision also refers to, I should say, is in context to a measuring tool. Well, we can qualify a measuring tool, based on the value of the graduates on the tool, which we talked about. So the smaller the graduates are, the more precise the tool is. And we're going to be talking about something called significant figures. That's also tied in with this. So very precise tools have very, very small graduates. And because they have very, very small graduates, they end up with a lot of significant figures. So for example, graduated cylinder, as you guys saw in our discussion on measurement, I think the graduate was by the ones, and then therefore the estimate went out to the tenths. This has a lot more precision than the beaker, that first beaker we looked at, which had graduates by the 50s and an estimate by the 5s. So that first tool, the graduated cylinder, would go out to the tenths place, versus the other one would only go out to the ones place, and specifically in an interval of 5. And then we have accuracy. Accuracy is how close a measurement, which we call the experimental value at times, to the accepted value. How close is the experiment value to the accepted value? In other words, how correct it is. So the accepted value is going to be some sort of number in the field of science that scientists have agreed upon as being the correct answer. Oftentimes in sophomore chem, we're going to tell you what the accepted value is, and you're going to make your comparison, your measurement, your final answer. You're going to make some sort of comparison to the what it should be, the accepted value. So we can do this mathematically. There's actually an equation for this that you'll use. So the percent error is equal to the absolute value of the actual value or the accepted value minus the experimental. So your value is the experimental, the actual is the accepted value, what it should be. So absolute value means it's going to be positive, positive only. So accepted or actual minus experimental divided by actual times 100 will give you a percentage, and this will be a mathematical way of expressing how accurate you were in your measurements. Okay. Dartboard analogy. I like to show the dartboard when talking about precision and accuracy. So it's a great visual to this. If we think of a dartboard, you have your bullseye and then you have outer rings around it. Take a look at this first image. We have all the marks hitting the bullseye and they're all very, very close together. This is an example of something being very accurate, assuming you're trying to hit the bullseye. So we're accurate in the sense that we hit the bullseye, and we're precise in the sense that all the marks are very, very close together. If we go to the right here, we notice all these marks are very, very close together, but they're on the outer circle. They're on the outer edge. So they're precise, but they're not accurate. The one down here is neither precise nor accurate. It just kind of marks all over the place. I'm sorry, this one's actually accurate, but not precise. Accurate in the sense that many of them are getting close to the bullseye. They're all within the first two circles here, but they're not precise because they're spread out, okay? And then, again, this one is neither precise nor accurate because you have marks all over the place, and most of them are really, really far away from the bullseye. So ideally, we aren't doing this, being neither precise nor accurate, okay? There's some value to having lots of precision, but not being accurate. Sometimes accuracy comes down to the constraints of the experiment. If you're using particular tools, you might be getting really consistent measurements with those tools, but the tools might not be appropriate for that particular experiment. And so it's no fault to the user, in that the fact that they're not being very accurate might be the constraints of the tool, but there's value in the sense that you're showing consistency. So being precise but not accurate is not always bad, okay? Especially if it's not accurate in a predictable fashion. Ideally, we want to be accurate and precise. That's the ideal. But again, oftentimes we're under the constraints of the tools and the procedure of a given experiment. Significant figures were mentioned a little bit in one of your assignments. These are linked to the measurement from a tool. Again, more precise tools yield more significant figures. So again, we identify when we're measuring something, the graduates that the object falls in between, and then we take an estimate. And all those numbers generally end up being significant. They end up being important because they come from that measuring tool. Now, if you don't have the tool in front of you, or if you didn't directly take the measurement, how do we identify how many significant figures a number has? Now, we're going to go through this with some activities next week, but here are the general rules that you're going to work with. There's 4 of them. Rule number 1, all non-zero numbers are significant. So in this example, notice all these numbers, 14225, 1999, all of these numbers are non-zeros, so they're all significant. So any number 1 through 9 will always be significant. Leading zeros are not significant. A leading zero means the number starts with a 0. So notice this number 0.125 starts with a 0. This 0 is not going to be significant. This number starts with a 0. Actually 3 zeros, 0.00, none of those are going to be significant. And this third one also starts with 2 zeros. Those are not going to be significant either, okay? We think of those as placeholder zeros. We're going to talk about that in an activity next week. these placeholder zeros, again, show you how small the measurement is, but they're not going to be considered significant. Zeros that are trapped between significant numbers are always significant. So like if they get sandwiched in between two significant, if they get sandwiched between significant digits, they are significant. So notice this 0 is trapped between the 4 and the 9. That will be significant. Notice this 0 is trapped between the 3 and the 2. That is also significant. And notice these two zeros are trapped between the two outer 2s. So all 4 of these digits will be significant. So we got 3 here, 3 here, and 4 here. And notice they're underlining the numbers that are significant. Trailing zeros are significant only if an explicit decimal point is present. So notice in this number 700, there is no decimal point present, which is 700. So therefore these zeros are not significant. But the answer, the number right here is 700 with a decimal point. All of these numbers are significant. So there's 3 significant figures. The zeros are significant because of the decimal point. So this is a little goofy in that just the placement of a decimal point has the effect on telling the reader whether or not numbers are significant or not. So oftentimes what you need to do, if you need to demonstrate from your measuring tool that you had 3 significant figures, the placement of a decimal point. 700 point will convey that, rather than 700 without it will not, okay? Sometimes scientific notation is a way to force a certain number of significant figures. So 700 written in this fashion has 1 significant figure, but 700 written in this fashion has 3, because it's 7.00 times 10 to the second. And notice we do not count numbers in the power 10 when looking at significant figures. It's just the number in front of the times. Okay, again, if this is not making a whole lot of sense, we will be hitting on this next week through a activity. So I promise it'll make more sense into next week. There's a couple of tricks with this, with identifying significant figures. There's the Atlantic rule and the Pacific rule. So if you think of the United States, you have the Atlantic side and the Pacific side. With the Atlantic rule, you think of like the East Coast. Think of A for absent. So if the decimal point is absent, okay, we're going to start from the right hand side of the number. So look at this number, 700 without a decimal point. Decimal point is absent. We're going to start on the right side where the Atlantic Ocean is. We're going to sweep to the left, and we skip all the zeros until we hit our first digit. That number and everything after it would be significant. If a decimal point is present, P for Pacific, think of like the Pacific Ocean. You're going to start on the Pacific side, and again, if a decimal point is present, P for present, Pacific Ocean, start from the left, scan the number from the left to the right until you hit your first significant digit. And that number and everything after it will be significant. So decimal point is present here in 700 points. So 7 and everything after it is going to be significant. So there are 3 significant figures there. And then computation. Just when you think you learn how to identify how many significant figures a number has, there's a couple rules for in terms of operations. Let's say you're multiplying or dividing, okay? When you're multiplying and dividing, let's say you're dividing 2 numbers, like in this example, you have to know how many significant figures are in each of the 2 numbers. So this first number has 2 and this number has 4. You do the calculation, you can punch into a calculator, and you're gonna need to round it to the least number of sig figs based on the 2 starting numbers. So we had 2 here and we had 4 here, so we're gonna round our number to 2 sig figs, okay? So the calculator may read 35.043, but we need to round it to 35 because 35 has 2 sig figs. Again, we're rounding to 2 sig figs because when we're looking at our starting numbers, 250 has 2 and 7.134 has 4. When you're adding and subtracting, it's not about significant figures, which one has the least number of significant figures. Now it's all about keeping the smallest number of decimal places, okay? So what do I mean by this? We look at this number, 73.147. What decimal place does that go to? It goes to the thousandths place. 52.1. What decimal place does that go to? It goes to the tenths place. Therefore, when you are adding these, okay. Oh, and there's a third number here too. That goes to the 10th, 100 thousandths, 10th, 100 thousandths place, okay. So thousandths place, tenths place, and 100 thousandths place, we're going to the smallest number of decimal places. So we're going to be forced to round our answer to the tenths place. So 125.301111 on the calculator needs to be rounded to the tenths place because that's the smallest decimal places of the choices given. So you would round your answer to 125.3. Okay, so the general rule of thumb is when you're doing computation, you can only be as precise as your least precise number that you're starting with, okay? So if you're not satisfied with the precision of your final answer in a computation, well, you're gonna have to use a more precise tool to grab a measurement from one of the starting values, okay? So again, it's kind of analogous to, you've heard the saying, your team is only as strong as the weakest link. Well, with doing computation, your precision of your final answer is only as precise, really, as your least precise starting number or starting numbers in your computation. So anyway, whip through that. Again, we will see you next week. This lecture is mainly for those who don't have class Thursday, so they can watch this video. And really, the only homework is to finish the measurement lab, to submit that onto MySJ. Let me know if you have any questions, and try to get that done before our next class. So we will see you next week.